This is going to start chapter 14 on sound. It's probably going to be your favorite chapter.
Why is it simple?
It's much better than what we've been doing.
Or were you being sarcastic?
No, not sarcastic.
I can't tell when you're being sarcastic.
Okay, so this will be 14.123, sound waves. It's on page 459. We talk about sound waves. We calculate the speed of sound through a medium and a temperature. So sound is going to change based on those things. So sound wave is a pressure wave. Imagine my vocal cords. I'm supplying energy into the vocal cords, and they vibrate, which causes a pressure wave. So some of the molecules in the wave are closer together than the other ones in the wave, right? Just like the slinky when we do a compression wave on the slinky, which you remember is a longitudinal wave. When I send a pulse through it, you can see. It's the same thing, but with air molecules. So the air molecules, they're squished up in the front and stretched out in the back, and they travel through the air. Molecules hit other molecules, which hit other molecules. They're transferring this wave, this energy, until it gets to your ear. And once it reaches your ear, it's very complicated. Your ear is very complicated, but if you break it down to its simplest form, it vibrates the gel and the little bones and the nerves in your ear, which send electrical impulses to your brain, which you interpret as sound. If you don't have any air for this pressure wave to flow through, you will not have any sound, no way to convey that sound. So that's why in space no one can hear you scream. It's because there's no air to transport that sound. You could make a sound, right, or you could vibrate that, but it's not going to vibrate any molecules. Make Benji's first.
You know how I saw in the video, like, the guy was flying away from the craft, and so he had let air off his suit. Why did you hear that? Is that realistic? Or?
Was it in a movie?
Like, he opened, like, something in his suit, and then the air started coming out, and so pushed him back towards the station.
Okay, well, the pushing back part, pushing him towards the station, that's momentum. That's conservation of momentum.
But
some mass and some velocity.
Because there's air inside.
Inside, he would hear it because he can hear, because that's traveling through air to get to his ear. But if you were outside of the suit, the sound would only travel through the air itself. And since the air is not anywhere, there's no air all the way up to your ear, the sound would only occur where that jet of air was.
So let's say, theoretically, that where the air was getting blasted, like if it was getting blasted right here, you wouldn't hear it. But if you moved your ear right there, you would hear it.
You would hear it because the sound wave would be able to reach your ear.
That's why you can hear things if you were on the other side of doors. If it's the door wood, and then that transfers the atoms into the air on the other side, and then it gives you just.
But you have to be close.
Or you can buy your electrical motor like your iPod and for that.
You get the electrical motor.
Are you recording this?
Yes.
Oh, cool.
Okay, I see blue cups, so I'm going to move on. To calculate pressure, it's going to be force over area. So if we're talking about pressure waves, you can calculate pressure as force over area. Think about high heel shoes versus big guy boot stomper things. Right? Flat shoes are a lot more comfortable because flat shoes have a lot more surface area. It's down here being surface area. And your force is distributed over that whole area, so your feet get less pressure, like, pounds per square inch is what pressure would be. Or for us, it's newtons per meters squared. If you think about a high heel, your area is just to the toe and to the back part of the high heel. So you get all that force, but on a much smaller area, so the pressure on your feet is much higher, which makes your feet hurt. So when we're measuring pressure, we usually either measure it in pascals or atmospheres. 1 times 10 to the negative 15 pascals is equal to 1 atmosphere. We're sitting in 1 atmosphere right now, so that would be the pressure of the air around us. And we need that amount of pressure, right? If you go up into space, there's no pressure, so your innards are going to want to become outers. Yeah?
Wait. So where did Pascal pull a number out that is 15
0.5
tens?
10 to the negative 15?
Yeah.
I'm not sure what that scale is based on. I think it's probably a derived number with like 1 Newton over 1 meter square or something like that. Is it like a derived unit? But I don't know.
For the version 2 for last year's, probably have a vacuum chamber or something.
Yeah, maybe. I don't know. Okay. So think of a sound wave as the force used to push those particles. I don't know what that's supposed to mean. Used to move particles distributed over particles? Oh, okay. So the force used to move particles, but it's distributed over all the particles. I think they're talking about pressure now. All right. So sound waves. There's different categories. There's 3 different types of sound waves. One is audible waves. This is what we can hear from 2 to 220,000 hertz. And this hertz is a frequency which we call pitch when it comes to sound. You may also think of it as the note, like a C or an A or an E. Then we have infrasonic, which means that it is very, very low notes. They are below the frequency that we can hear, so lower than 20 hertz. And then we have ultrasonic waves, which are higher, so they'll be higher than 20,000 hertz. These are very, very high notes. These are like your dog whistles. Sure.
What can you hear infrasonic ones?
Infrasonic.
Pelicans.
I mean, honestly, it just has to be sensitive enough. Like, let's see, frequency, wavelength. The lower the frequency, the higher the wavelength. Lower.
Just big stuff.
Yeah.
Big things in low sounds.
Yeah. Low frequency would be a large wavelength, and things with large wavelengths have to have large receivers. So, you're right, big ears. Here is a picture of a tuning fork. This would be the wave. This is more of the pressure compression wave. You can see high density, low density, high density, low density. So that's like this would be a wave, or this would be a wave. So as the tuning fork continues to vibrate, the compressions, it's going to push the air this way, and then it's going to create like a void in the air as it goes back and forth. We'll grab a tuning fork for you. Good luck. And you will get to play with these next week. We were so excited. Doesn't we said next week? So this is a tuning fork, and this is a tuning fork activator. You should not hit the tuning fork on the edge of the table or a desk. Also, you should probably not hit yourself with it. But it damages the tuning fork, and if you get chips and notches, then it's not going to be the same tone that it's supposed to be. On it, you can see a note and a frequency. So this says C1024. So that 1024 is the frequency, the hertz that it is. And C would be like the note that it plays. So it's not very loud. You should not do that, no. I can do 2 of them at the same time, though. Don't hit them.
Sounds like he's having fun.
You may also hit them on the bottom of your shoe, and that makes it work better if you're.
We could create some little orchestra.
But one time we're allowed to do rhythmic noises, so they're sound useful on the
It's still going.
Oh, I want to get one.
This one has a very high frequency.
It's still going.
Ooh, move it past your ear.
Okay.
How does this one? Or like 4.
And you can trade, you know.
It's still going.
All right, so ultrasound is used widely in the medical field. They image things that X-rays can't. So X-rays would be an electromagnetic wave, like light, and it's a very short light wave. So they take things like bones, so very dense things they can bounce off of. Ultrasound gives you more of a picture. That's like what you would use to see the baby that's inside of you. So not just the bones, but you're seeing things bouncing off like the head of the baby and the skin of the baby. So it's gentler. It won't cause any sort of radiation or anything like that, which is what the harm of X-rays is, that it is electromagnetic radiation, where this is just pressure waves, sound waves. So it scatters these sound waves. You take pictures of like spleens and hearts and stuff.
It's funny because if you shake it back and forth, it also changes.
Also, the sound is that you put the tube.
If you make it like this to your ear instead of this way,
If you do it this way, it really hurts.
Drop it.
I continue this
All right, so let's calculate the speed of sound. The speed of sound at room temperature is 343 degrees. At 0 degrees Celsius, so freezing, it would be, I think it's 333 degrees, so 330 meters per second. So think about when lightning strikes. You see the lightning strike, and then you hear the thunder much later. You can actually count how long it takes. And I think it's about like every second is a mile-ish,
Yeah.
something like that. And you guys get a lot of thunderstorms here in Florida,
Yes.
where it's not like that normally. Like before I came to Florida, I probably witnessed maybe about 5 thunderstorms in my entire life. Yeah, I witnessed about 5 the first week I was here. So you can calculate this actually, the actual velocity of the speed of sound if you could mark, when you see the lightning, count the seconds. Well, sorry, the speed of sound is 343. You could count the seconds and then figure out how many meters away that would be. And then you can convert to miles if you wanted to. It's about 1 second as a mile. It's a pretty good one. So the speed of sound, which is just going to be distance over time. All right, I know you guys are playing with your tuning forks, but you still got to use your cups. Thank you. So echoes. The only tricky thing about echoes is that you have to double the distance, because if you say something, it's going to go that distance to the wall and then back to your ear. So whenever you have an echo problem, just remember that your distance is actually doubled from whatever it's bouncing off.
Wait, is it doubled after it gets bounced off or before? Like, doesn't matter.
If you're measuring it up, from where you stand, the echo goes this way and comes back to you. Yep. So velocity equals distance over time. If you're trying to locate this thing, you're standing here.
Okay.
You release a sound, and it's going to come back. So this will be 343, and let's say this is 10 meters. This will be 20 in the amount of, let's say it's 10 seconds. Or something like that. It wouldn't be 10 seconds, but whatever.
Another question.
So your actual distance would end up having to be 10. So you find the distance and then divide by 2. Yes.
So if you want to go faster than the speed of sound, you just have to go faster than 343 meters.
Yep.
Yeah.
That's not even a lot.
Yeah, airplanes do it all the time.
It is if you're human.
Yes.
No, my
That's why
grandma
I-
saw a video where it showed them breaking the sound barrier and like the pressure wave, and she's just like, I didn't know it did that. Like,
Whoa.
Well, Mach speed, like Mach 1 is the speed of sound. Mach 2 would be twice the speed of sound.
I was just thinking about Mach 5, and I can't remember where I remember that from.
Yep.
Mach 5, Mach 6.
Okay.
Speed racer.
So we're going to look at the equation for wavelength and frequency. Velocity is wavelength times frequency. So wavelength is in meters, and frequency is in hertz, which is 1 over seconds. So this ends up being meters per second for the velocity. Remember that frequency again is the pitch of the note, or the, it's, like middle C or whatever. That has a specific frequency.
Just hide the cup, that way I don't have to look. If it's not on the table, then it's not there.
And this funny little wave, the wave with the kickstand, is called lambda.
To me, it looks like an upside down line.
It is.
A backwards upside down line.
Now, depending on how thick the medium is, that will change its speed of sound. So the denser the medium, the faster it moves. If you put your ear down to a train track and there's a train coming, you're going to hear the train through the track before you're going to hear it through the air, because the track is much denser than the air is. So that means that the speed of sound through water is going to be a lot faster than through air. Yes.
So you could hear noise through me faster.
Yes.
If Mike said or something, and then let's say Nick was like right here, he would hear it through me before he hears it through me.
Sure. I'm not sure why you'd be that close to you, but yeah, that's what we're getting at. Okay. Now, this equation is used to find, this one's not used by us very often. I wouldn't worry about this too much. It's not going to be on the AP test. But I did want to include it in there because they talked about it a little bit. This is the velocity. Your B is going to be your bulk modulus for fluids and your Young's modulus for solids. Now, we did not cover these things, but they're properties of fluids and solids. So how dense it is, how squishy it is, because density doesn't necessarily mean how squishy it is. So we have these bulk and shear and Young's modulus, and it's like how much you can deform the object. So this is rubber; it's going to deform a little bit. My duck is going to have a really, really squishy. So it's not necessarily just how dense it is, but also how squishy it is. And that is just dependent on your object. Now, there are some ways to calculate it, but we did not cover this, so you won't need to do that. And the row down here, the row on this equation is a little funky looking. It just kind of looks like a weird P, but it actually is like a curly P. That's rho right there. And that is its density. So density is just kilograms per meters cubed. So your mass per volume, just like any other density you've ever seen. So these modulus values, they're really not on the AP exam. I wouldn't worry about it too much. The speed of sound and temperature. The sound is going to vary directly with temperature. So the hotter it is, the faster it's going to travel. And this is because the air is moving more, so it transfers the pressure wave faster. The hotter the object is, the more the molecules are moving around. So like air molecules are moving around pretty fast, and then liquid, they're not moving around as much, and then solid, they're just kind of vibrating right there. They're stuck. Yes.
So something with it like 0 Kelvin, there wouldn't be any sound.
Well, we have to move the particle, and that movement of the particle would heat it up.
And therefore,
So therefore, no.
0 Kelvin.
Yeah, absolutely zero.
Actually, they have been able to cool stuff down to 0 Kelvin. There's a paper, if you look on Google, about negative temperatures. They were able to cool it past 0 Kelvin into the negative things, and they said it was hotter than the sun, like any temperature they've ever measured before, like the suns and stars and stuff. So it's cyclical. It was so cold that it's burning.
It's like
the
dry
way
ice. Like
that
if you touch
ice
dry ice,
burns.
it's going to burn you.
It gets more and then increases or something.
So is that vice versa? Like if something's really hot, it's gonna make you feel cold?
I mean, if you could get it all the way up there, maybe it would go range around. You have to read the paper. It was very interesting, though.
Well, I mean, like when you stick your hand in the really hot water, what does it feel like?
Pain.
It's just pain. Yes, it does feel cold, but that's not because it's actually cold. It's because of your nerves. It's because it's killing the cells. Okay, to calculate the speed of sound in a fluid, you actually are going to use this one. You're going to use 331, so this is the speed of sound, times the square root, the temperature of the fluid, over 270.
How is this one different from the other one?
It is the same thing, but it's specific for fluids.
Okay, that just happened.
Since we're not really going to deal with these bulk and Young modulus stuff, this one is putting the values in for you. So this is the one you'll probably use. Now, you need to make sure that you're putting your temperatures into Kelvin. You should not be putting them into Celsius or Fahrenheit. They need to be converted to Kelvin first.
Oh, crap.
Kelvin is
C plus 273? Yes.
cold or hot?
What?
Wait,
What are you talking about now?
What's the Kelvin?
Okay, so
Well, I was
0 Kelvin is so cold that nothing is moving, but 0 Celsius is just the more.
So right now the room is probably like 100 Kelvin.
It
Like
is.
300 something.
It's like 301 Kelvin.
The room feels hotter just because you're
Kelvin
saying
would
that.
be absolute.
Kind of like a
Did you
second
just say
of time.
100 Kelvin?
Speaking of converting, yay, version. This is your Fahrenheit to Celsius and your Celsius to Kelvin.
No Fahrenheit to go? No Fahrenheit to go?
You don't get one of those.
Well, you could just apply it by putting
In
that
theory.
equation right in there, inside that figure one.
Although I would definitely check that equation because I just taught that to my other students and I had it backwards.
I thought it was just
I think that is backwards.
I think it is backwards. I wouldn't make that one.
Wait,
I think it's
Does that
5
mean 0 Fahrenheit?
Yeah, it should be 5/9 and then TF minus 32. I gotta fix that. That's weird. Okay, so TC equals 5/9 TF minus 32. Yeah, I definitely had it backwards.
Oh, so it's in terms.
Yeah, because you got to do it first before you multiply. It's a good thing I taught temperature today in my other classes.
That was him not doing what he was told not. That was him doing what he was told not to do.
Wait, not doing what he was not supposed to do.
Yes.
Or was he not doing something not?
Now we're negative.
Yes.
There's like a point up there. It's like not
0?
up there.
Oh.
I have
That's something I wanted to do. You wave your hands around.
it's like it just like floats air around it. You just stand there.
But that's not how it's there.
Okay, so Bill, you wanted an equation from that'll change Fahrenheit to Celsius.
Did you just
Stop
plug
it.
the?
Celsius.
What Celsius?
Did you just plug in?
Oh wait. Oh,
I did. And I got
Kelvin.
5 nines Fahrenheit plus 241.15 will equal the Celsius.
Wait, that one does not fit up there. That's confusing.
I know. That's what I'm saying. That one's wrong. This one's right. I had switched it up in the.
Oh wait, that's in parentheses.
Yes.
Oh darn it! That totally throws up my calculations.
That's probably.
Just
the
use
other one.
brackets.
I don't know why I can't find this temperature version of this, but let me try a different one.
Well,
Let's try this one. 12.
I will
What are you doing?
Okay. So correction.
What did you say? Oh yeah, your temperature thing is right.
The CIA spent
Oh, it's on the temperature and words right here.
figure out what would happen.
It says track 32 when you're going to Fahrenheit to Celsius. Track 32 for then multiplied by 5 divided by. Yeah, that one's right. Yep, that one's right. Okay, the one on the board is right. That one is just, I think you just switched. Yeah, I switched the F and the C. Okay, so we're going to do a practice here. You're standing in the courtyard and singing a lovely note at 900 hertz.
And it is this lovely note.
That's not 900 hertz, though.
Yes, it is.
9 over 5.
You multiply it by like 8.
Wait. So the equation is 9 over 5.
The equation is the one on the board.
5.
The temperature that day is 95 degrees Fahrenheit. The note echoes off a wall and you hear it 0.77 seconds later. What's the speed of sound that day?
Okay. I have an equation for this. Hey, wait, the temperature doesn't even matter.
Yes, that's.
It does.
No, wait.
It does.
Wait. Hold on. Do you have an equation that just tells us how to get it out of air?
The one that I said was for a fluid is just the temperature and speed normally. Sound is a fluid, that's why. I was thinking water. Yes, sound is a fluid. Air is a fluid. So for this one,
I like that question. It says, what is the speed of sound that day? I like the equation.
thank you. Velocity. I wrote this question, that's why it's a little tricky. T over 270. So our velocity is going to be 331 meters per second. We need to convert to Kelvin.
Which is 308.15.
308.15 degrees Kelvin over 270.
Right.
I didn't think 308. Oh, wait.
The answer should be 351.664.
I agree.
Yeah.
You concur.
Good? Okay. How far away from the wall is it?
Okay. Got this. I have an answer.
You have an answer already.
It is a right answer. Yes.
you get 135 meters?
Yes, indeed.
Good. And it's because the sound has to travel from the person to whatever the object is and back. So it's traveling twice the distance. So if you want to know just one distance, you got to divide it by 2, 135. All right, C, what is the wavelength of the sound wave? We already know the velocity is 351. What is the frequency? 900.
Aha. Right. Yes.
Should get something like 24 meters. Good? Easy? Not too bad.